Last week we were doing mechanical translational, and then this week we're gonna do rotational system, and we're also gonna do gear transfer for system with gears. Okay, so we're gonna do rotational. Okay, last week we did the mechanical, where I said we have three elements, where we have mass, spring, and a damper. So here on rotational, we're also going to have the three elements, which is going to be a damper, a moment of inertia, and a spring. Okay, we're also going to have three elements here. Here we're going to have the moment of inertia. Or should I say inertia? Yeah. And then we're gonna also have a stiffness, spring, and a damper. Remember, on the translational, we were using damper as FV, and then here on rotational, we're gonna use damper as D. Okay, so let's say we have a spring like this, it's connected to a wall. And then remember, here it's a rotation, so we're gonna have a torque and an angular displacement. So let's say we have a spring with a torque moving clockwise like this, and then we also have a displacement like this, a theta t like this. And then now we're gonna generate an equation for torque. So our torque here is gonna be T of T equals to K for what? For stiffness, for spring is stiffness, multiplied by what? By the theta of T, theta T, okay? And then now we're gonna introduce Laplace both sides. Remember this topic, that's where we use Laplace transform. So we're gonna introduce Laplace both sides. When we introduce Laplace, we're gonna have the T of S is equals to K theta of S. Remember, the S is stand for what? For Laplace operator. Okay, now when we have a spring, our equation is gonna look like this. It's gonna be K multiplied by theta T, and then when we introduce Laplace, we're gonna have the T of S is equals to K multiplied by theta of S. Okay, and then now let's say we have a damper. Let's say we'll be given a damper like this. Here on our damper, still we have a torque and an angular displacement. So now when we generate equation for damper, so it's going to be a T of T equals to, it's going to be a damper, okay? Damper multiplied by what? The derivative, the first derivative of theta. Oh, sorry. So it's going to be the D of theta, the first derivative of angular displacement, over dt. Or we can write it as d theta dot of t to show that is what? Its first derivative. And then when we introduce Laplace both sides, we're going to have the big letter T with S equals to d of S theta of S, like this. So that's when we introduce Laplace both sides. Okay, so Laplace of first derivative is S theta of S. Okay, and now let's say we are given an inertia. So if we are given inertia, our equation is gonna look like this. So let's say we have we have the inertia. So let's say we have our inertia like this. Okay, and then we have the torque and angular displacement. So let's say this is our inertia, okay? And when we generate the equation, we're gonna have the T of T equals to inertia multiplied by what? The second derivative of what? Of theta. So it's gonna be the d squared theta of T over dt squared, or we can write it as T of T equals to J theta dot dot, okay, just to show it's the second derivative. And then when we introduce Laplace both sides, we're gonna have the big letter T of S equals to J. Derivative of theta dot dot is what is gonna be the S squared theta of S, like this. So when we have the moment of inertia, our equation is supposed to look like this. And then when we have the damper, it's going to be the ds theta s when we introduce Laplace, okay? And then when we have a spring, it's going to be k theta of s when we introduce Laplace, okay? That's how this rotational system works, okay? So now let's do an example and show you how to solve this rotational figure when we are given it, and then they say, okay, they ask us to determine the transfer function. They also, okay, determine the transfer function of g of s is equal to theta of s over t of s. So most of the time they will ask you to determine the transfer function under this rotational system. So now let's say we have this figure. So we're going to do an example. So let's say we have the inertia. We have the inertia here. Okay. And then we have a spring and a damper like this. Okay. And a damper like this, okay? And then we have another spring there at the end. We have a spring here, then it's connected to a wall, and then in between we have a damper, okay? Then it's connected to a wall here. So, and then here we are given that we have a torque which is moving clockwise, the torque which is moving clockwise, and then we also have, this is T, then we also have a theta. Let's say this is our theta 1, and then this is T, okay? And then also in between of a spring and a damper and the other spring, we have a theta 2. A theta 2 here, okay? So let's say here our inertia is 1, okay, and then our spring here is also 1, our damper is 1. Let's say all of them are equals to 1, okay, with their unit, with their the unit of moment, it's kg meter square. And then for spring, we know for spring is Newton per meter, and then for damper so. Okay, so first thing that we have to do here, we're gonna draw a free body diagram of our inertia, okay? So we have inertia here. The first thing that we're gonna do, we're gonna draw this inertia where we have a torque and a theta 1, okay? So when the torque is moving clockwise, which means also the inertia is gonna also move clockwise. Our J, we're gonna represent our inertia as J. So if the torque is moving clockwise, even the J is gonna move clockwise, but the damper and the spring is gonna oppose. Okay? So which means spring and a damper, they're going to oppose the direction. So we're gonna have the damper and a spring, okay, which is going to oppose. It's gonna be opposing, okay. And then when we want to write our equation, remember the moment is gonna go with the theta dot dot, the second derivative, okay. And the damper is what? It's first derivative. And remember, this damper is between theta 1 and theta 2. Okay, it's between these two. So which means when we write our equation, it's going to be damper into what? Into theta dot 1 minus theta dot 2. Okay, because the damper and the spring are what? Are in between theta 1 and theta 2. Even on K, stiffness is also between theta 1 and theta 2. So we're going to have the difference, okay? We're going to have the difference between theta 1 and theta 2. Which means K is going to be K into theta 1 minus theta 2, okay? So this is what I'm saying. Our K is going to be theta 1 minus theta 2. And then our damper is going to be a theta 1 dot minus theta 2 dot, okay? So that's how we're going to draw our free body diagram, okay? Remember, just remember, when the torque is moving clockwise, this it's supposed to be like this, okay? It's moving anti-clockwise. Sorry. Just know, okay, the damper and the spring is gonna be opposing all the time. So from drawing the free body diagram, we're gonna write our equation. So it's gonna be a total of torque, okay, which is gonna be equals to what? To inertia dot dot, like this, okay, to J. So on the left, we're gonna add all the torque, all the energy, which is the damper and what? And stiffness. So remember, it's opposing. We're gonna take clockwise as positive and anti-clockwise as negative. Okay, so we're going to have the torque, which is going clockwise. So it's gonna be torque, this one, let's say it's T1, okay? So we're gonna have T1, and then we're gonna have minus what? Damper, minus D into theta 1 dot, okay, minus theta 2 dot, okay. Even this spring is opposing, so it's going to be minus K into theta 1 minus theta 2, okay. And then all equals to, we don't still have other energy, okay. So it's going to be all equals to what? Equals to moment, the J theta dot dot, equals to J theta what? Dot dot, okay, like this. And then from here, we're gonna introduce Laplace. Remember, here we're working with theta 1, so we're gonna introduce Laplace both side, okay. We're gonna introduce Laplace both side. Remember, I said when we have the d theta dot 1, d theta dot 1 is the same as ds theta, and then if we have the theta dot dot, is the same as what? As s squared theta, okay. And then this theta is just gonna be a theta of s, okay. Now moving forward, we're gonna introduce Laplace both side. When we introduce Laplace both side, okay, before introducing Laplace, we can just simplify this. We can just simplify this. So let's simplify. We're gonna have the t. We're gonna have t1 minus d theta 1 dot minus d theta 2 dot minus k theta 1 minus k theta 2 all equals to j theta dot dot one, okay, like this. So when we introduce Laplace both side, we're gonna have, remember here we were working with the linear differential equation, so it's t1 of t and then theta 1 of t, okay, theta 2 of t, theta 1 of t, then theta 2 of t, and then theta 1 of t. t. Okay, and now we're gonna introduce Laplace both sides. So when we introduce Laplace both sides, we're gonna have Laplace of t is gonna be a t of s. Remember the s, it shows Laplace operator. Laplace of damper theta dot is gonna be a negative damper s theta 1 of s, to show that what we are doing Laplace. Okay, here it's gonna be the same, so it's gonna be minus d s theta 2, okay, of s. And then here theta 1 is just gonna be negative k theta 1 of s, and then negative k theta 2 of s, like this, equals to the derivative of theta dot dot is going to be the j s squared theta 1 of s, like this. Okay, remember the question here will be asking us to determine transfer function of theta over t. Okay, so here we have this equation. What we can do, we can just group the theta 1 together and the theta 2 together. Okay, so we're gonna take the damper and the stiffness to the right, so we're gonna be left with t of s equals to js squared theta 1 of s plus d s theta 1 of s plus d s theta 2 of s, and then we have plus k theta 1 of s, and then we have another k theta 2 of s, like this. Okay, and then after here we're gonna take theta 1 as a common factor, because we have the theta 1 and the theta 1, and we also have the theta 2 and the theta 2. Okay, so this is what we're going to do. So it's gonna be, we're gonna have the t of s equals to theta 1 into j s squared, and then we have another theta 1 here plus ds, and another theta 1 here, and then we have plus k, like this. Okay, and then we have plus, and then we're going to take out the common factor of theta 2. We're going to have the theta 2 into ds plus k, like this. Okay, and then in most cases they'll say, okay, determine transfer function of theta 2 over t, like this. Okay, so they'll ask us to determine that, and remember here we have theta 1 and theta 2, which means we're going to have what, two equations. So this one is going to be our first equation where we were focusing on theta 1, and then now we're going to focus on theta 2. Okay, we're going to focus on theta 2, and then we find another equation. After getting the equation, that's where we're going to determine what, the theta 2 over t, the transfer function of what, of theta 2 over t. Okay, that's what we are going to do. So now we are done with the first theta, and then now let's do the second theta. Remember our diagram looked like this. So we were focused on this one. Okay, and now we're gonna focus on this theta 2. So we're gonna draw what we call a free body diagram of theta 2. We're gonna draw a free body diagram of theta 2. So our free body diagram, let's say we have another what we call inertia here, because we have the theta 2 here. So our second free body diagram, when we're focusing on theta 1, so this one, it was for theta 1, and then now this one is going to be for theta 2. Okay, so here we're still going to do the same. The damper and remember the torque is moving clockwise, the damper and the spring is going to be opposing. Okay, so our inertia is also going to be going the same direction as what, as torque. Okay, so let's say we're gonna have what do you call, this. But remember here we're not given the inertia, so it's just gonna be imaginary, okay? And then I just want us to I'm just making it to help us to determine the equation of motion, okay? So showing you, okay, if we had the moment of inertia, it was gonna moving the same direction as what? As torque. Okay, from here we're gonna check, or okay, when the torque is moving clockwise, the damper and the spring, this damper and the spring is gonna be opposing again. So we're going to have the D into theta 2 minus theta 1, theta 2 dot minus theta 1 dot forward for the second theta, okay? And then we're also gonna have the stiffness, this stiffness, which is opposing, okay? And then it's gonna be K into theta 2 minus theta 1, okay, like this. And remember guys, we have this damper, we also have this stiffness, so we're gonna call it K1 and this one is gonna be K1, this one is gonna be D1, and then this one is gonna be D2, and then this one is gonna be K2, okay? So moving forward, remember here we're drawing a free body diagram focusing on what? On theta 2. So we're gonna have this spring and damper because it's connected to theta 2, so it's going to be between theta 1 and theta 2. That's why we have theta 2 minus theta 1, okay? And then now we're going to focus on this spring, on K2. Also K2 is going to be opposing, but here it's going to be K2 multiplied by what? By theta 2. And the damper, also the damper is going to be opposing, so we're going to have the damper as D2 multiplied by theta dot 2, okay? So in our equation of motion, we're going to have the damper 1 and damper 2. We're also going to have K1 and K2. Remember here, we don't have, we don't have torque, we also don't have the inertia, we're not given there, okay? Here the free body diagram is just helping us to determine the energy that is acting on theta 2, okay? So we have the damper and the spring, damper 1, damper 2, and damper 3. Now let's do equation using the second free body diagram, okay? So for theta 2, remember we have the first equation is this one, and then now let's do the second equation so that we can find the transfer function of theta 2 over t, theta 2 over t, okay? So what we have on that diagram, we have the imaginary inertia, and then we have the damper D1 with theta 2 dot minus theta 1 dot, and then we also have another damper as D2 theta dot 2, and then we have the stiffness K into theta 2 minus theta 1, okay? Then we have another K as K2 theta 2, like this, okay? So this is what we're going to do. They're all going anti-clockwise. So remember our equation it's T is equals to J theta dot dot, but here we don't have this theta dot dot, this J, okay? We don't have it, so it's gonna be equals to 0. So here we're gonna add all the energies, okay? So we're gonna, actually I was supposed to say D, oh no, it's fine. So we're gonna add all the energies and equals to the inertia, but now we don't have the inertia. So we're going to have the negative D into theta 2 dot minus theta 1 dot, okay? And then minus D2 theta 2 dot, okay? And then we have minus K2 theta 2 minus K1 theta 2 minus theta 1, all equals to 0. Remember here on theta 2 we don't have moment, we don't have inertia. On theta 2, we don't have inertia, we also don't have torque. Okay, so what we're going to do here, we're going to introduce Laplace. We're going to introduce Laplace in both sides. So here, in both damper and spring. Okay, so here we're going to have a negative d1s theta 2, then we're also going to have d1s theta 1. So we introduce Laplace, so we're going to have a negative d1s theta 2 of s plus, we're multiplying, plus ds theta 1s. Okay, here we're going to have minus d2s theta 2 of s. Okay, plus minus so we're going to have minus k 2 theta 2 of s. Okay, then minus k1 theta 2 of s plus k1 theta 1 of s is equal to 0. And then now from here we can group the theta 1 and theta 2 together. After grouping them, we're gonna use the first equation and substitute back so that we can get what? A theta 2 over t. Okay, the transfer function of theta 2 over t. Okay, so here we're gonna take out the common factor of theta 1 of s, and then we're gonna have a ds. Okay, here's another theta 1. Theta 1 is this one. We also have this one. Okay, plus k1. Okay, and then for theta 2, let's say plus theta 2. For theta 2, we have a negative ds. We also have another negative 2ds. This is its d1. Then minus d2s. Okay, and then we have another k theta 2, negative k2 and negative k1, all equals to 0. Okay, and then now we have this equation. Remember when we started this figure, we said the damper, the spring, and the inertia, they are all equals to 1. Okay, so they are all equals to 1. Now let's rewrite the equations that we have. The first equation, it was like this. The first equation was t of s equals to a theta 1 of s into js squared plus ds plus k, and then it was plus theta 2 into ds plus k. Okay, this was our first equation. Then our second equation, it's theta 1 into ds plus k plus theta 2 into minus ds minus k, so. Okay. So it's theta 1 into ds plus k plus theta 2 into minus 1 d1s minus d2s minus k2 minus k1. Okay, all equals to 0. And then I was saying, okay, when we started, we say the j, the d, and the k, they are all equals to 1, which means the first equation is gonna look like this. It's gonna be the t of s equals to theta 1 of s. The j is 1, the d is 1, the k is 1, so it's gonna be into s squared plus s plus 1. Okay, like this, plus theta 2 into S plus 1. Okay, we were substituting the values of D and the K and J. And then for equation 2, is going to be theta 1 into S plus 1. Okay, plus theta 2 into minus S minus 1, like this, all equals to 0. Okay, and then this one is going to be minus 2S minus 2. So theta 1 into S plus 1 plus theta 2 into minus 2S minus 2, like this, all equals to 0. And then now remember, we are looking for what? For theta 2 over T. So what we can do, we can use these two equations, first and the second equation. We can make the second equation theta 1, substitute the formula, and then we substitute back so that we can get what? A theta 2 over T. So moving forward, we're going to take the second equation and make theta 1 substitute the formula, okay? And make theta 1 substitute the formula, and then after that we're going to substitute that equation back to equation 1 so that we can get theta 2 over T, okay? So we're going to take the second equation and going to go and make it substitute the formula. So the second equation we had so what is theta 2? Theta 1 into S plus 1, okay? And then we're going to make theta 1 substitute the formula. So what we're going to do is going to be a theta 1 into S plus 1, okay? All equals to a negative theta 2 into negative 2S minus 2, like this. And then we're going to divide both sides by what? By S plus 1. So it's going to have theta 1 is equals to a negative theta 2 into negative 2S minus 2 over S plus 1. Like this. And then here on top we can take out a negative 2 as a common factor. So we're gonna have a negative multiplied by a negative 2 theta 2 into S plus 1, because we take out a negative 2 as a common factor, all over S plus 1. The negative times negative is positive, and then S plus 1 and S plus 1 is going to cancel each other. So our theta 1 is going to be equals to what? To 2 theta 2 theta 2. Okay, so this one we're going to take it as equation 3. And then therefore we're going to take this equation 3 and substitute what? Back to our first equation. Our first equation, it was T of S equals to a theta 1 into S squared plus S plus 1, and then plus theta 2 into S plus 1. S plus 1. Remember, we are looking for what? We are looking for theta 2 over T. So now, wherever there is theta 1, we're going to substitute with what? With theta 2. With 2 theta 2. So we're going to have the T of S equals to 2 theta 2 into S2 S squared plus S plus 1 plus theta 2 into S plus 1. Okay, and then now we're gonna calculate this. We're gonna take out theta 2 as a common factor, and then after that we're gonna do what? We're gonna divide both sides by T, and then we get the value of theta 2 over T. Okay, now moving forward, we're going to have something like this. The T of S equals to 2 theta 2 into S squared plus S plus 1 plus what? Plus theta 2 s plus 1. Okay, plus theta 2 into s plus 1. And then from here we can start by multiplying both sides by this 2 by s squared plus s plus 1. So we're gonna have a theta 2 into 2s squared plus 2s plus 2 like this. And from here what we're going to do, we're going to take out theta 2 as a common factor. So we're going to have the t of s equals to theta 2 into 2 of s squared plus 2s plus 2 plus s plus 1 like this. Okay, and then now we can get what? Theta 2 over t. So to get theta 2 over t, we're going to divide both sides by what? By t. So we're going to have the t of s divided by t of s. And this side we're going to left with 1. And then here we're going to have theta 2 over t of s multiplied by this. Let's say this is a, multiplied by a. Okay, and therefore we're going to have a theta 2 over t as what? As a 1 over a. Remember, our a is 2s squared plus 2s plus 2 plus s plus 1 like this. Okay, so this is how we do the rotational. We'll be given the diagram and then note, okay, when we have the inertia, we write our inertia as j theta dot dot, and then we're gonna introduce Laplace both sides. When we have a spring, we're gonna write it as k theta, and then we introduce Laplace, gonna be k theta of s. And then if we have a damper is d theta dot, and then when we introduce Laplace is what? Is ds theta. Okay, and then now moving forward, we're gonna do what we call the transfer functions for system with gears, where we have gears. Okay, and then after here we're gonna do an example with gears. After doing the example with gears, that's where we're gonna stop. Okay, so now we're gonna do transfer function. So let's say we are given two gears, the small and the big one. So let's say we have the gears, okay, like they're connected. Okay, don't mind my gears. So let's say the first gear, it has the radius of r1, and then the second one has radius r2. Okay, and then they are moving, so we're gonna have the torque 1 and a theta 1. Then this one is gonna be opposing. If this one is moving the other side, the bigger one is gonna move. It's gonna be opposing each other. Okay, like this. We're gonna have t2 and theta 2. Okay, so here we're gonna assume there's no energy in these gears. Okay, and then also what we're gonna assume, gonna say, okay, the distance traveled by the first gear is equals the distance traveled by what? By the second gear. So the r1 theta 1 is equals to what? To r2 theta 2. So the distance that the first gear is traveling is the same as is equals to the distance that the second gear is the distance of first gear is equals to the distance of second gear. Okay, and then we're also gonna assume that before assuming the energy, we're gonna make the theta 2 over theta 1 subject the formula, which means we're gonna divide both sides by what? By theta 1. Okay, remember we want theta 2 over theta 1. We're gonna make theta 2 over theta 1, substitute the formula. Theta 2 over theta 1, substitute the formula. And then after that, we're gonna be left with R1 over R2, okay? And then from here, we're saying, okay, the angular velocity is equals to the radius. Also here, the number of teeth of gear 1 is equals to this radius. So we're gonna have the N1 over N2. N1 is for number of teeth, okay? Number of teeth of gears. And then now when we assume that there's no energy, the torque T1 is gonna be equals to what? To T2 when we assume that there's no what? There's no energy. So the T1 theta 1 is equals to T2 theta 2, and therefore we can simplify and get what? A T2 over T1 equals to what? Theta 1 over theta 2, and then equals to what? To N2 over N1. Okay, so we're gonna use these equations when we are solving. Okay, we're gonna use this type of equation, the theta R1 theta 1, but most of the time we're gonna be using this two, the T1 theta 1 and then T2 theta 2, number of teeth over another number of teeth. Okay, so now let's do an example of this gear. So this gear will be doing them on a rotational system. So we'll be having the gear, we'll also be having let's say a damper and a spring and inertia. Okay, so what we're going to do here, we're going to do an example and show you how this transfer function for system with gear works. Okay, so now let's say we have this example. So okay, and another thing on the figure, the gear is gonna be represented like this. Let's say we'll be having gears. So this one is gonna be gear 1, and then this one is gonna be gear 2, number of teeth N1 and N2. So the gears are gonna be represented like this. This is the symbol for what? For gears in a figure. When we have given a figure, don't get confused when you see something like this. Just know we have gears. Okay, so even here they will ask us to determine what? The transfer function. So okay, determine transfer function of maybe theta over t, theta 3 over t, theta 2 over t, something like that, theta 1 over t1. So it's the same thing under under translational mechanical rotational system and transfer function gear. They'll be asking you guys to determine the transfer function, so which is gonna be a theta over t. Is an angular displacement over what? Over torque. So moving forward, let's do an example of gear. So let's say we have a gear like this, where we have torque and an angular displacement. Okay, here, and then let's say this one is gonna be our first gear, and then this one is gonna be our second gear, N2, like this. And then this second gear is connected to inertia. We have inertia. Okay, and then here on inertia we have a damper and a spring, like this. Okay, a damper and a spring which is connected to the wall. Okay, and then here we have a theta 2. Here we have theta 1 and torque, which is just torque. Okay, so when we are given something like this, that's okay, determine transfer function. The first thing that you have to do, you're gonna be looking for torque, you're gonna looking for damper, total torque, total damper, total stiffness. Okay, this is what we're going to do. So we're going to have the TE equals to, we're gonna have the damper DE equals to, gonna also have the KE, gonna also have the JE, like this. So for torque, we're gonna check, okay, our torque is here with what? With gears. So if we have the gears, we're gonna multiply our torque with the number of teeth. Okay, so this gear, it's moving from where? From 1 to 2. From 1 to 2. So in the ratio, when we write ratio, it's gonna be N2 over what? N1. 1 to 2. When we write the ratio, fraction, is going to be N2 over N1. So the total torque here is going to be the torque, this torque, multiplied by the number of teeth, this N, number of teeth of gears. So it's moving from 1 to 2. So when we write in a ratio form, it's going to be N2 over N1, like this, okay? N2 over N1, okay? And then now when it comes to damper, we're going to have the damper here. Remember, the damper is not connected to the gear. If it was connected to the gears, it was connected to the gears, we were going to write our damper as D multiplied by what? By N2 over N1 squared. Even if if our K was connected to the gears, we're going to have the K multiplied by what? By N2 over N1 squared. Our J is also connected to this gear. So our J is also going to be what? It's going to be J N2 over N1 squared, okay? If these dampers and spring, they were close to the gears, we were going to write them like this. But since they are not, so it's going to be just what? A damper, which is moving with what? With theta 2, which move with what? With theta 2. So it's going to be theta 2, and then K, here we have dot, and then K also going to be moving with what? With theta 2. And then even this damper, inertia, moment of inertia, is moving with that, with what? With theta 2. So it's going to be a theta 2 dot here on the damper. Okay, so after here, we're gonna add these two. Remember, our equation is T equals to what? To J theta dot. Okay, and then we're gonna add all the energies this side and then equate to this, and then we introduce what? Laplace transform. After introducing Laplace transform, that's where we write it with the S operator. After there, we're gonna simplify. Okay, the difference here is just gears. When we have gears, okay, so when we have gears, we multiply our torque, our damper, and spring with gears. And then in the value, if the damper is close to the gears, we're gonna say D multiplied by N2 over N1 squared, okay? And then for K also is gonna be N2 over N1 what? Squared, okay? So there is this paper of another figure from, I think it's test preparation number 1, where it has a gear and the rotational system. It's from test preparation where we have gears. I think we had 4 gears. We had N1, N2, N3, N4. We have 4 gears, number of teeth, N1, 2, and 4. So it looks like this, where we have the first gear, and then the first one, it was connected to what? To inertia. Okay, like this, and the inertia is connected to what? To damper. They are connected in series like this. Okay, and then here we have another gear. Here we have another gear with what? With torque. So this one is our first gear, which is equals to 11. Then this one is our second gear, which is equals to what? Was 33. And then they say our inertia is 1, and then our damper is 2, and then our spring is 3. Okay, and then this one is what? It's N3, number of teeth number 3, which is equals to what? Equals to 50. Okay, and then we also have another one here. Actually, it's connected straight to this one. Even this one is connected straight to this one. Is it straight? But somewhere there. And then we have another one with here we have a theta L of T. And then we have a damper like this. Okay. Then here we have what? N4. They say N4 equals to 40. Okay. Remember I said when we have the gears, the first thing that we do, we're gonna get all the the torque, all the damper, all the stiffness, and all the moment of inertia. So we're going to have the TE, the DE, the KE, and JE. Okay, I'm gonna check. So we have a torque. Okay, we have a torque like this. Sorry, just a moment. So sorry, here we have a torque here. So our torque is connected to these two gears, like it's moving what clockwise. It's gonna be moving clockwise. So it's this two gear and this one. And remember, when this gear moves, also this one is gonna move. It's gonna be opposing. Okay, so it's gonna be moving all together. So when it comes to T, we're going to have T from what? From N2 to N1, from N3 to N4. So we're gonna multiply it. Remember, it's from 2 to 1, and then we're gonna write it in a ratio form. So it's gonna be N2 over N1 multiplied by from N3 to N4. So it's gonna be N4 over N3. So this is how we're gonna write our torque. Okay, our torque, we're gonna multiply it with gear. So it's from gear 2 to 1, gear 3 to 4. Remember, when the gear moves, also the other one moves. That's why we're multiplying this number of teeth. Okay, and then for DE, the damper, we have damper 1 and damper 2. This damper thing, it was 0.04. Yeah, it's 0.04. Okay, and then for damper, you can see here, this damper is connected to this gear. Okay, it's connected to this gear. So it's gonna be, let's say this one is gonna be our D2, and then this one is gonna be our D1. So D2 is gonna be multiplied with the damper, with the number of teeth, because it's connected. So we're gonna have N4 over N3 squared. Remember, I said when we have a damper, we squared the number of teeth. Okay, and then after here, what we're going to do, we have another damper, so we're going to add this damper, so it's in between, so it's going to be plus D1. Okay, then we are done with the damper. And then when it comes to spring, you can see the spring is connected to this gear 3, and then gear 3 is also connected to what? It moves together with gear 4. So the stiffness is going to be K multiplied by what? By N4 over N3. And remember, when we write the damper in the spring, we squared. Okay, and then JE, the moment of inertia. The inertia, remember, this inertia is connected to what? It's connected to what? To gear 2. So we're gonna have J N2 over N1 like this. And after here, we're gonna now write the equation, our equation. We're gonna write our equation. So remember, our equation, it's T equals to what? J theta dot dot, J theta dot dot, like this. Okay, So we have the t, which is multiplied by n2 over n1 and n3. Is it n3? n4. n4 over n3. Or we have the damper and the spring. We have the damper and the spring. And remember, if the torque is moving clockwise, the damper and the spring is going to be what? It's going to be opposing. So we're going to have a minus dE, because we know dE is equals to what? d2 n over 4 over n4 over n3 squared. Okay, so minus dE minus ke. Okay, like this. We're gonna have this, and then equals to je theta dot dot. Okay, theta dot dot. Oh, here we can just write te instead of substituting, just to show you we're gonna write it like how. So it's te minus de minus ke equals to je theta dot dot. Remember, it's theta L. It's theta L. Okay, so now that's where we're gonna introduce what? The Laplace transform. We're gonna introduce Laplace transform, and then we're gonna have the t of s. Oh, sorry guys, we have the theta dot here, the theta L. Okay, so we're gonna have Laplace of t. It's gonna be t of s minus dE of s theta L minus ke theta L, or equals to je s squared theta L. Okay, and now we can take out the theta L. Remember here, I think on that equation they want us to determine the theta L over t, and then here we can take this to the other side. So we're gonna have the te of s equals to je s squared theta L plus de s theta L plus ke theta L, like this. And then we can take out the theta L as a common factor. Then we have t s is equals to theta L into, gonna have jes squared plus des plus ke, like this. And then we're gonna divide both sides so that we can get what? The theta L over t. So we're gonna divide both sides by t, and then we're gonna end up with this. So we're gonna have the theta L over t e of s equals to, remember here at t we multiply it with the number of gears, where we had n2 over n1 multiplied by n4 over n3. Okay, so here it's gonna be the number of gears divided by what? Divided by je s squared plus des, okay, plus ke, like this. So you're just gonna substitute the values of je, de, and ke, and then you're gonna substitute the values of number of gears. So the number of gears here, n2, it was 33, so it's 33 over 11 multiplied by n4, which is 40 over 50, all divided by the je. We were given j as 1, so it's going to be 1 squared plus the damper. Remember here at damper we have the other damper multiplied by number of gears, so you're going to substitute the number of gears and multiply with that damper, and then you get the value. So we're going to have the value here, which is going to be multiplied by s plus ke, which is what? Which is 3. 3 multiplied by number of teeth. So even here we're going to multiply it with number of teeth, and then our transfer function is going to be looking like this. Okay, so this is how we do it when we have gears. We are on a rotational system. Okay, so we're going to stop here. All the best guys with the test. Bye.
Bye bye.